Howdy. This video is on gases and the ideal gas law. Gas is an important phase of matter. We are surrounded by gases. The ideal gas law's assumptions yield a relatively accurate description of gases under normal conditions. After watching this video, you should be able to describe what gases are like at the atomic level and macroscopically. You should be able to describe the assumptions of the ideal gas law. You should be able to use the ideal gas law equation to calculate pressure, volume, number of moles, and temperature. And so this is a decent simulation of water vapor at room temperature in 1 atmosphere. And so you notice that the particles are very separate. For a gas, it's mostly volume. And so the gas particles do not interact strongly with each other. And so gases, they're mostly free space. They can expand infinitely. They occupy containers uniformly and completely. They diffuse and mix rapidly. For an ideal gas, the intermolecular forces between the gas particles and the volume of the gas particles themselves are negligible. And so again, if you look at the gas, mostly empty space, not a lot of interaction between the particles. And so that's why we can assume that intermolecular forces are negligible. And the volume of the particles themselves make up a very small fraction of the total volume. And that's why we can assume the volume of the gas particles is negligible. Gases can be monatomic or polyatomic. Monatomic just means composed of one atom. So noble gases are all monatomic. They're just single atoms floating around. Some polyatomic gases include hydrogen, nitrogen, ammonia, carbon monoxide, oxygen, fluorine, chlorine, and carbon dioxide. And so polyatomic just means composed of more than one atom. Oxygen is diatomic. Carbon dioxide is triatomic, and you could call ammonia tetraatomic. But if you get something hot enough, it will either decompose or become a gas. So for example, water vapor is just a gas. Now I want you to know the formula for these common gases. And so if you're asked a question about oxygen gas, you have to know that corresponds to O2, or nitrogen gas corresponds to N2. All gases can be condensed. So if you get cold enough, the gas will become either solid or liquid. Now, helium has the lowest boiling point of any element. This boiling point is 4.2 Kelvin. And if you remember, the only intermolecular forces it has is London dispersion, and it's very small. Remember, for London dispersion, the more vast is strong interaction. Well, helium is not very strong, so it's going to have a very weak London dispersion interaction, and hence a very low boiling point. As you go down in this list, you're getting to bigger atoms with stronger interactions and hence higher boiling points. The composition of gas at dry air and sea level, about 80% is nitrogen, about 20% is oxygen. You have a little bit of argon, a little bit of carbon dioxide. Now, pressure from a gas results from hitting the walls of a container. And so we have a container and the gas particles will hit the walls. And so it's just going to be force over surface area. You can also think about pressure as resulting from all the mass of all the gas above us, and that gives us atmospheric pressure. And so it's kind of interesting. For atmospheric pressure, the higher the altitude, the lower the atmospheric pressure. Also, at high altitudes, you have a small partial pressure of oxygen gas, which can lead to what's referred to as altitude sickness. Now, if you remember, liquid boils when the vapor pressure equals the external pressure. And so at the top of Everest, the external pressure is just 240 torr. At sea level, it's about 760 torr. And so at sea level, water boils at 100 degrees Celsius. At the top of Everest, water actually boils at 70 degrees Celsius. Because again, water boils when the vapor pressure equals the external pressure. And at high altitudes, your external pressure is going to be much lower. And so I mentioned that pressure, you can think about in two ways. One is the mass of all the air above us, but also as resulting from the particles hitting the wall of the container. And so pressure is equal to force divided by area. Force is equal to mass times acceleration. And so if our mass is in kilograms and our acceleration is meters per second squared, and if our area is meters squared, this meters will cancel with one of those meters. We'll be left with kilogram per meter per second squared. Now, that's actually the unit for a Pascal. Now, there's a few different units for gases that we can use. We can use Pascal. We can use what's called a bar, which is equal to 10 to the 5 pascals. We can use an atmosphere. There's also torr, and there's pounds per square inch, PSI. And so an argon gas cylinder has a pressure of 22.5 pounds per square inch. Convert this to kilopascal. And so we're given this equivalence. So 101.325 kilopascal equals 14.7 pounds per square inch. Now, whenever you're given an equation like this, you can always make a fraction, which you can use to change the units. And so if we divide both sides by 14.7 pounds per square inch, then we get this. Now, this fraction is just equal to 1. You can always multiply things by 1. Now, we're given as 22.5 pounds per square inch. So that goes here. And so we need the pounds per square inch at the bottom. So if we multiply this times the fraction we just created, the pounds per square inch will cancel, and we'll be left with kilopascals. But please always make sure that you watch your units. And so for this can under normal circumstances, you have gas particles hitting the outside of the can, you have gas particles hitting the inside of the can, and actually the pressure on the inside and outside of the can are equivalent, and so nothing happens to the can. Now what we can do though is we can pull vacuum and remove some of the contents from inside the can, and so fewer gas particles will hit the inside walls of the container. And so by removing the gas from the inside of the can, there's nothing to oppose the gas from the outside hitting the walls of the container, and it actually causes the can to crumple. It's kind of cool. We can do a similar experiment here. If we take the soda pop can, we add a little bit of water, we heat it, producing steam. The steam will displace the air, and so after a while we'll have just steam inside the can. Now, if we then put the can in ice water, that will condense the steam into water, and you'll reduce the pressure.
A small amount of liquid water is placed in a can and boiled. The can fills with water vapor. Quickly inverting the can into ice water causes that vapor to condense, and atmospheric pressure crushes the can.
Kind of cool. And so you can think about, the technique we used, and you think, okay, maybe could we crush something larger, like a 50-gallon drum using this technique? And so he had added water. He heated the water, producing steam. The steam displaces the air from his 50-gallon drums. And then after a while, he turns off the burner and seals the 50-gallon drum. And so right now there should just be steam in the 50-gallon drum. Now on the tray, he has ice. And so he's going to put the 50-gallon drum in the ice and try to condense the steam. And that's just due to the atmospheric pressure. And so we're all under a decent amount of pressure, but we get used to it and we don't really realize it. And so we could do a soda pop can, we can do a 50-gallon drum. Could we do something larger, like a train tank car? This is almost a half-inch of steel. I forget exactly how much. And actually, yeah. So what happened was someone cleaned out the tank car using steam. They tried to be conscientious by closing all the valves, left, and when they came back the next day, this is what happened. And so this is just due to external pressure of the gases. Could we crush something larger like a submarine? Nah. The submarines are just designed to withstand a tremendous amount of pressure. And so gas properties can be modeled. The models depend on volume, temperature, number of moles, and the pressure. And so the ideal gas law, PV equals nRT, pressure times volume equals number of moles times gas constant times temperature. Now, please remember temperature always has to be in units Kelvin. Now, the gas constant, there's actually 5 different values for the gas constant depending on the units. And so if your pressure is atmospheres, you'd use this one. If your pressure is in bars, you use that one. If your pressure is kilopascal, or if your pressure is in torr. Now, you should notice that on your worksheet, all 5 values of the gas constant are given. So ideal gas law, P equals nRT, the approximations, intermolecular forces are negligible. And again, you saw from the simulation that for gas, it's mostly empty space. And the volume of the gas particles is negligible. Again, for gas, it's mostly empty space. And so the volume of the gas particles themselves makes up a very small amount of the total volume. Now, at low temperature, intermolecular forces become important. Remember, all gases will condense at low enough temperature. And so the ideal gas law breaks down at low temperature. It also breaks down at high pressure where the volume of the gas particles is no longer negligible. Now, before the ideal gas law was developed, Boyle's law, Charles' law, and Avogadro's law were developed. Now, if you notice, PV equals nRT, we solve for V, we get this. And so Boyle's law has V is inversely proportional to P. Charles' law is V is proportional to T, and Avogadro's law is V is proportional to N. So Boyle's, Charles, and Avogadro's law are all in the ideal gas law. And so I don't need you to remember which one's Boyle's, Charles, Avogadro's, but I do want you to be able to use the ideal gas law to solve for pressure, volume, number of moles, or temperature. Should also mention that for all 4 of these, notice that the identity of the gas does not matter. And so if you're dealing with hydrogen or nitrogen, it does not matter as long as you know PV equals nRT. And so Boyle's law, volume is inversely proportional to the pressure. So if you increase the pressure, you're reducing the volume. Or if you increase the volume, you'll reduce the pressure.
A decrease in the volume of a gas sample results in an increase in pressure because the gas particles will hit the walls of the container more often.
And so the reason that volume and pressure are inversely proportional, if number of moles and temperature are constant, you reduce the volume, then the particles hit the walls more often, and so smaller V corresponds to higher P. Again, pressure is just due to the gas particles hitting the walls of the container.
When the gas in this cylinder is compressed at constant temperature, the gas pressure increases as the volume decreases. Robert Boyle, experimenting with air, found that the product of the pressure times the volume is a constant at constant temperature. Dividing through by the pressure, we see that volume is linearly related to the reciprocal of the pressure. These pressure-volume relationships are expressed by Boyle's law.
Charles' law says that the volume is proportional to temperature. And so if number of moles of pressure is constant, if you increase the temperature, the volume will increase. If you reduce the temperature, the volume will get smaller.
Temperature and volume are directly related. As heat is added to a sealed syringe, the volume of the air in the syringe increases. A plot of gas temperature and volume demonstrates that the relationship between them is linear. If we extrapolate the line down to a temperature of absolute zero, in principle, the gas has no volume.
And so for an ideal gas, zero temperature would correspond to zero volume. But at some point, all real gases will no longer behave ideally. So high temperature, they'll behave ideally. You lower the temperature enough, eventually it will stop behaving like an ideal gas. And so again, here we have volume versus temperature. We have for oxygen, for hydrogen. And again, it stops behaving like ideal gas at some point. And so you'll never get to zero Kelvin and zero volume.
The Dewar flask or thermos contains liquid nitrogen at a temperature of 77 kelvins. The balloon has been blown up with air.
So by pouring liquid nitrogen on the balloon, you're making the gas particles colder. And so they hit the walls of the container less often with less energy. And so the balloon gets smaller. And so lower temperature corresponds to lower volume. Higher temperature corresponds to higher volume if the number of moles and the pressure are constant. And then finally, Avogadro's law just says volume is proportional. This symbol here means proportional to the number of moles if pressure and temperature are constant. And so if you have twice as many molecules, you should have twice the volume. And so here we have 8 molecules and 4 molecules. And if we added them, we would get 12 molecules and 3 times the volume of the small container here. And then it's going to react, and then you'll see.
Quantity and volume are directly related. If we take 8 molecules of H2 and combine them with 4 molecules of O2, we get 12 molecules and a combined volume. If we then react the mixture, we end up with 8 molecules of gaseous H2O, which occupies the same volume as 8 molecules of any other gas.
This is kind of cool. Here we have 8 molecules of H2. Here we have 8 molecules of H2O. If the pressure and temperature is the same, the volume should be exactly the same, even though we have a lot more mass here, right? So for H2O, you have a lot more mass than you do for H2. But the volume depends just on the number of particles, not the identity of the particles. And so ideal gas law incorporates Boyle's law, Charles' law, and Avogadro's law. The identity of the gas does not matter. And I want to make sure that you're able to use PV equals nRT. Again, you should be able to solve for any of those parameters. So for instance, you could be asked, if the temperature of gas is doubled while the volume is kept constant, what happens to the pressure? Well, we saw that volume and temperature are proportional. Volume's constant. What happens to the pressure? And so higher temperature should lead to a higher pressure if volume number of moles are constant. And so PV equals nRT. P is directly proportional to temperature in units Kelvin. And so if you double the temperature in units Kelvin, you should double the pressure. What would happen if the temperature of gas is tripled, 300 Kelvin to 900 Kelvin, while the pressure is kept constant? What happens to the volume? Well, the volume should triple. We could also say, okay, if the temperature of gas is quadrupled from 100 degrees Celsius to 400 degrees Celsius, while the pressure is kept constant, what happens to the volume? Now, this one's a little tricky. You might want to say it is a factor of 4, but remember, temperature has to be in units Kelvin. And so to answer this question, we have to convert from Celsius to Kelvin by adding 273. And so 273 plus 100 is 373. 273 plus 400 gives us 673. And so the new volume is going to be equal to 1.8 times the old volume. So please remember, temperature has to be in Kelvin. And so what are some properties of gases? There's a lot of free space. Gas is typically mostly free space. They can expand infinitely. They occupy containers uniformly and completely. They diffuse and mix rapidly. What are the assumptions for ideal gas law? Intermolecular forces are negligible. Again, you don't see a lot of particles interacting with each other. And the volume of the particles themselves is negligible. Again, the volume of the particles themselves make a very small fraction of the total volume. Under what conditions does the gas behave most like an ideal gas? And so that would be high temperature, where you don't have to worry about intermolecular forces, and low pressure, where we don't have to worry about the volume of the gas particles. So ideal gas law, P equals nRT. We assume intermolecular forces are negligible. We assume the volume of the gas particles are negligible. Ideal gas law will break down at low temperatures because all gases do condense eventually. And ideal gas law breaks down at high pressures when the volume of the gas particles is no longer negligible. I hope that was helpful.